Good morning to the attendees. Receive a cordial greeting from the IEEE GRSS Geoscience and Remote Sensing Society Student Technical Chapter of the University of El Salvador. My name is Lizardo Arias, a member of the latter student chapter and a student of electrical engineering. I would like to thank you for attending our webinar titled Remote Sensing Applications for Environment and Sustainability. Without further ado, we will start the webinar. The webinar will be given by Ricardo Dalagnol, who has a bachelor's in engineering in environmental engineering, a PhD in remote sensing from the National Institute for Space Research, INPE, Brazil. He is currently working as a postdoctoral researcher at the University of California, Los Angeles, UCLA, and also is a research affiliate of the NASA Jet Propulsion Laboratory in the California Institute of Technology, also known as Caltech. He has experience with a diverse range of applications in geosciences, with a focus on tropical ecology, nature conservation, and environmental monitoring in the Amazon forest. He specializes in conducting quantitative research using advanced types of data, such as high-resolution satellite optical and airborne LiDAR data, as well as methods such as deep learning convolutional neural networks. Without further ado, Mr. Ricardo, you can start the webinar.
Thank you, Lizardo. Thank you for the invitation and all the organization from the IEEE GRSS. I think you guys are doing an awesome job on bringing this kind of content for the faculty. I think this is a great way to expand what you can get from your own university and look abroad and look into other stuff. So I wish I could present in Spanish. Perhaps we would understand a bit better. Pero mi español is no bueno. So I'm presenting in English. My name is Ricardo Dallagnol. As Lizardo said, I'll present you a bit of my research on this last 10 years. And yeah, if you want to ask something, you can just write in the chat, and we can talk about that by the end. So let's take off. This is what you can see. It's the launch of the Landsat 9 satellite from last year. This is just a crop of a few minutes of this launch. If you are a nerd in Earth observation and satellite stuff like me, you probably start to look for this kind of stuff. You may see in about 3 hours there's a launch of SpaceX rocket, putting like 50 or so satellites and stuff. So look for the YouTube channel from SpaceX. In about 3 hours, they'll have a launch. And talking a bit about me before we start on the more technical stuff, I'm an environmental engineering from Brazil. I'm almost a forest engineer as well, so I love to study, to talk about forests. And my master's and my PhD I've done in INPE in Brazil. This is a great institute to learn about remote sensing. We have a great remote sensing graduate program over there. It also welcome international students. I remember seeing students from outside Brazil over there. I've worked at Leeds, UK during my PhD as well. And right now I am a postdoc researcher in the US. I just arrived here early this year and starting to learn stuff, how to work here, and that's it. And besides work, I also like to do lots of other stuff. We always talk about work, but we like to code and do stuff like this, but we also like to drink some beer, play some games, and look at beautiful landscapes such as these two locations in Brazil. And the key topics I bring you today on this presentation is more technical stuff about remote sensing, Earth observation, applications, algorithms, all of that. But what I wanted to give you, I think this last couple of years that we had this pandemics going, and it's about to rise again, unfortunately. But I think as undergraduates and graduates, you may have lose opportunities to interact with other people, to go to conferences, to go to see different stuff. It's a unique experience to go to a congress and look and open your mind to a lot of stuff. Perhaps you went to some online conference as well, but I mean, what I wanted to show is different applications in the field of Earth observation, remote sensing, talking about some of the challenges that we want to solve, some applications that I've done in my career, talk a bit about techniques that are important, that are upcoming, so new techniques that you as engineers and in different areas such as from electrical to other stuff, engineer, civil or environmental like me, that you may want to know and apply on your job, and some skills that you should learn along the way to be successful in um, getting a good job after you finish your bachelor or your master's or PhD. So I think one important thing that I think we talk about sustainability all over and over. In my bachelor, more than 10 years ago, 15 years ago, we talk about sustainability, and I had no idea what's that. And but now it seems that the world is starting to organize this better. We have this thing called Sustainable Development Goals. If you never looked for this, take a moment, write this down, and look for this afterwards. It's how countries are guiding their research, their efforts to improve our lives. So you may do your work, your research, focused on some aspects of these sustainable development goals. Um, for example, you may work on subjects related to climate action, so like bringing estimates of carbon emissions from different aspects, from cities, from cars, from industries, from deforestation, which is an active problem in tropical countries like ours, from Brazil, from El Salvador as well. Or you can look for other stuff like life below water. If you work with this kind of stuff, you can uh, there's a variety of things you can uh, pursue related to these goals, and companies are looking on ways to say, oh, our company is helping the world through this. So this is something for you to take a look and make sure you can locate how your work, how your job can help towards this. And I put this that in perspective, that big problems such as those that I presented may require big data. And we talk a lot, we see a lot about big data here. Big data, there about the amount of data we have, for example, from social networks and all of that. People are using that nowadays. But we also have big data in remote sensing, and this can bring us intelligence information on natural resources that can guide decision making relating those sustainable development goals that I was talking towards, for example, land use, land cover change. So how your landscape is changing from forests to crops to pastures, or how another kind of natural vegetation is transforming over the landscape. But also in cities, how the urban planning, like how a city is improving more on the industrial um, setup to more like increasing um, in energy, lots of different stuff. And I put here some topics that I used to work, like forest dynamics, forest diversity. And another perspective here inside cities, you have intelligence information that are very useful for um, decision making, such as knowing where are the buildings, which types of buildings, do you have solar panels. This is related to electrical engineering probably a lot. Where are those located? Where are optimal locations to place those kind of solar panels? This is something I was talking to Lizardo the other day, so I remember now. Um, And so this information this data can bring information to decision making. And the traditional big data is separated in these three categories: volume, variety, and velocity, how you can deal with that. And in remote sensing, there's a paper that talks about this, and it says that the remote sensing big data may be divided in multi-source, because you have several satellites, several types of data, such as optical data, like what we can see, radar data, LiDAR data. There's a lot of types of data. Multi-scale, because you can see data in a few meters resolution, but also in hundreds of meters. And each type of data is maybe good for one or other application. It's also high dimensionality, which is related to the volume. You can have several bands, spectral bands, to work with, and you need to know how to deal with that. You may have mixture in the pixels that you are looking in an image. In one pixel of a 30-meter resolution from Landsat, for example, you may have forest, but you can also have a part of a building. So you have this kind of stuff to deal, as well as of other non-linear characteristics. So it's a very complex type of data. And when we look to all this in another perspective, from resolution to like coarser resolution to higher resolution, also in different temporal resolution, like you see images every day from planet satellites, to every 16 days, like Landsat. And you may have images from drones that you can just fly a drone here and monitor something. So there's a huge complexity on using this, and you as an engineer, you need to know how to use that well. So here gives you some perspective, three scales that you may work, and what may be useful for each scale. And another thing that come not recently anymore, it's just about 5 years or maybe more, we have, with some lines of code, we can have the world at our hands, such as this code. You input that into Earth Engine, Google Earth Engine, and you just have, for example, the whole elevation for the whole world. This is something that 10 years ago, when I started my master's, I would imagine this would be possible, but it's standard right now. You need to know about this. You need to know how to work with this. So if you are pursuing a career at Earth observation, you have to take a look on Google Earth Engine and other kinds of cloud processing platforms, that you can have all types of satellite data and process that on the cloud. And one analogy here that I like to make is the data is similar to oil. I do not create this. I got this from other literature, but people says that data is like oil. Both are fuels, but alone they do not mean much. But if we refine that oil, if we refine that data, we may gather some information from it that can be useful. So satellite images alone does not mean anything. Like, you can have gigabytes, petabytes, terabytes of data. They do not mean anything. But what's important, what we extract from it, and that's where your analytical skill come in hands. And so that's why we talk now about some applications that are interesting. For example, mapping land cover and use dynamics. And here I put one example from my master's that it's about that 10 years ago. I started to go to tropical forests to learn about the complexity of those environments, such as we have immense amounts of forest, but we also have land cover changes, such as forests being converted to crops or pastures. I expect that in El Salvador you also have these happening. this economical growth, but coming at the cost of losing your natural resources from forests. So this can be an issue. Deforestation. We also have logging, like people cutting just a few large important trees from the forest. And I went there and started to understand these processes. And the aim of this work was to create maps like this, which nowadays I do not think this is looking very good. It's kind of noisy, but at the moment, this was a very important map for me. It was one of the outputs of my master's work, where I combined this understanding from the field, looking at forests at different stages of regeneration, from initial secondary forest to advanced, and here is the primary forest, like the intact forest, and trying to map that, because it's important to know where the forests are regenerating as well. When they are regenerating, they are gaining carbon, they are sequestering carbon from the atmosphere. And getting these satellite images with this knowledge from the field, putting this together with some kind of model. And I used some neural networks, which was is not a new concept. It's a concept from the 1980s, but nowadays it's becoming more and more and more useful, bringing more techniques. Neural networks are being used in everything that we know today. And a few years later, just to put this in perspective, my work was done in some point in the middle of the Amazon, but we have now cloud processing platforms such as Google Earth Engine that allows mapping in large scale very fast. And Map Biomas is one of those initiatives from Brazil. It's not governmental, it's independent, but they provide these land cover maps. And I think they are expanding this to other countries in South America and probably around Central America as well. So now we have maps on large scale. This is just unimaginable, like at this fine scale, the 30-meter, like 10 years ago, we wouldn't think about that. And using these land cover maps, we some studies have brought, like, okay, we have the land cover map for different years. We can track the forest, how it's progressing over time. An area is forest, then it's deforested. And perhaps a few years later, it's forest again because it's regrowing. Somebody didn't care for that area, it's regrowing again. So if the map shows it's forest, you can keep track of that, and you can calculate the age of those secondary forests, for example, and you can make maps out of that. And this paper showed that, and afterwards we used that in a paper that we published to calculate how much carbon those forests were accumulating over time, and providing like estimates of carbon accumulation, and how these secondary forests can help mitigate uh, uh, climate, like climate change. So, for example, if we maintain the secondary forests, maintain, I mean, we do not cut them down anymore, that were present in 2017 in the Brazilian Amazon, we could accumulate this amount of carbon until 2030, which would contribute to 5% of the net emissions reduction target. So this geospatial data provides these tools for us to create this information that it's every country is looking for. How we can absorb carbon from the atmosphere, how we can reduce the heating of the atmosphere, reduce climate change effects. So to bring this to your attention, that this data can help us do that. Here's are some technical aspects how we did that, but in summary, we gathered biomass data from the European Space Agency, ESA. They have maps for biomass for the whole world. You can get that for your country and look at that on different years and see how biomass is changing in your forest. And we did that, and we looked for different climate predictors, environmental predictors such as radiation, precipitation, and we look how the carbon is changing with this environmental and climate patterns. And then you can build this type of curves to see, oh, forest is gaining more carbon in, I don't know, wetter places, you know. So you can build this kind of stuff combining different data sets. And this is important because every country is looking for this, and companies are also starting to realize this, and this is called the carbon market. Carbon credits is where a forest is being preserved, and for that, companies want to pay for you to preserve those forests, because the companies are, for example, are not carbon neutral. They are spending more carbon than they are saving, let's say. And so they want to say, okay, we want to be carbon neutral. We don't want to hurt the world. So they pay for whoever is protecting these forests. So this is a growing market. Also, besides that, in parallel to that, you have active forest plantations going on. So new forests that are going to accumulate carbon. And it's a similar approach. You want to measure how much carbon you're accumulating. So this is a thing that you might be looking forward. And to look at forests, you can look at other ways, for example, with LiDAR data, which are lasers that you emit in direction to the forest with airplanes and also with satellites, and you can have this very precise representation of the forest and build and do ecology studies, but also this kind of more carbon oriented studies. Also, you can track illegal activities. For example, this is a case where I try to map logging. So when people extract just a few trees from the forest, in one date you have this tree around here, in the other date you don't have the tree anymore, so you see a difference in height. So if the area suddenly opens a space in the forest, we call this a gap, that tree is gone. So you can see that with LiDAR data on the top, which represents the height of the trees, and you can see that with very high resolution data on the bottom, which is like the optical data, such as from world view satellites, what we can see in like Google Maps and Google Earth. And you can do that also with more coarser resolution, but you may lose, for example, the finer details of single trees. When we extrapolate this, we can see areas that were expected to be logged in legal logging, like forest concessions, but also places that were outside of these areas, which are potential like illegal activities. So we can monitor our forests to track for that. Here's another study that I brought you here. You also using LiDAR data. If you see on this map on the right, there's these small lines, which are, each of those are one flight line of LiDAR data. I will not go into the specifics of these studies. You can look at that afterwards. But here's just to say, like, to process all this data, you need to use things like parallel processing, because otherwise you may lose lots of time with just one one flight line, then you go to another flight line. So you need to have these tricks like parallel processing. Your computer processor, you can put more than one task to be processed on the same time. So you split the job in different tasks and you get that much faster. This is from the same study, just showing some results on the whole Brazilian Amazon. And what I did with that, I had the 600 and something flight lines. What I did with that is I extrapolated that, I upscaled that to the whole Amazon. And I did that again, looking for predictors from the climate and the environment. And you build some spatial models. You can build some, like, imagine a regression, like a linear regression, but imagine you can relate a predictor from climate, let's say precipitation, to the variable you want to estimate. Then if you have lots of samples, you can build this model and extrapolate over bigger regions, and you can do that for a country and get the results, understand that you need. We also have the orbital LiDAR sampling. So this previous LiDAR data, you could see individual trees. With the orbital LiDAR, you cannot see individual trees anymore, but you can have data over much larger locations. The data will look like this samples of height. So you can see for this line, you have like different elevation. You can also extract the terrain from this if you are interested on that. You can just subtract the forest, throw the forest away, and look for the terrain. Perhaps this is what you're interested. You can get the LiDAR data to do that. And we have this all over the globe right now. We have this data called JEDI. It's a acronym for I forgot the name for that, but it's a name to remember from Star Wars. Yeah. So, but it's a LiDAR on board the International Space Station, and it's gathering data all over the globe. So you see, you have data over El Salvador, over South America, everywhere. It's not regular distributed. You do not have like pixels like Landsat, but you can have like samples, and you can use that to build this kind of spatial models to extrapolate afterwards. And here's another perspective. Different kind of data is like more on a time series. And in electrical engineering, you may look at this kind of signal like a temporal signal to understand something. This is the same type of stuff. You have an image, but if you look to each pixel, you look for something like this. It's a signal that has a frequency, has we call like a seasonality, because it's how the signal is changing over the seasons. You have a tendency, which is this T, which is maybe increasing or maybe it's flat. And for example, in this case, I wanted to find when the signal changed, like an abrupt change on the signal, which was a decrease in the near infrared band from MODIS satellite. Because when the signal dropped, it was this green vegetation and dropped to this bluish colors. So when you look here, it's green, 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 green. Sometime soon, I hope, it will become blue. It's when the signal dropped. In this case, it was when these populations of bamboo species, when they died, they become very dry and they just vanish from the top of the forest. That's what you see in this image. And that's what I tracked from using this kind of time series analysis. And afterwards, mapping that, I could make this map highlighting each one of those areas that we could see that effect. And you could do this kind of stuff to detect other changes in the landscape, such as deforestation, for example. It's forest. When the signal drops, perhaps it's deforestation. And now talking about artificial intelligence, there's this guy, Andrew Ng. It's one of the most famous guys from machine learning in the educational perspective. If you go to Coursera website, you may find a course from Andrew. It's machine learning something. It's a very good course. It's free. And you may learn a lot of machine learning techniques for different kinds of applications, not for remote sensing specifically, but of different kinds. And it's the new electricity. That's what he says, because it's within everything. You have that in Facebook, in games. You have that to detect person, dogs. You have that in cars. You have that in design of tools. You have that to check for, you imagine you have like an airplane and you have to inspect if the airplane is, everything's all right from the airplane. You don't want to spend like hours looking for the airplane. You have to look it fast. So you may just use a sensor to look for the airplane, and you plot the data and you run some algorithm to look, okay, this is something weird. Maybe there's a fracture in the material. Oh, we may be worried or not. So you use machine learning for that. And one of the state-of-the-art methods for image segmentation, now talking more about remote sensing and all kind of images that we may use these methods, is it's within the deep learning part of the machine learning, but it's the UNet model. The UNet model is this one you're seeing here. So it was the model that we use in this paper. The objective of this paper was to find palm trees. So these palm trees were in the top of the canopy. You want to map that, and this model is based on a series of convolutions, which are represented by these squares here, which you look for the images, but not just one pixel at a time. You look for windows, and so it's like when we look for an image, we just do not look for one pixel. We look like the context, the texture. So this is what these kind of models do. So imagine you have this is an example, this little robot. You have this filter, which is like this window that goes through the image. One tries to find horizontal lines, the other tries to find vertical lines. And when you pass this filter through this image, you get this result. If you combine these two, you get this little robot. But the issue is, what if you don't know which filters you want to use? Which features from the image, like the bands, are important to highlight what you want to see in the image. For example, we want to see the palm trees. A simple filter won't find this, but the thing that the deep learning do, these convolutional neural networks do, it learns the filters. So it learns which little square of weights you go through the image, and learns which windows brings you the object that you want to detect. So there's a lot of technical stuff on this, but if you are interested on working with images, finding objects in images that may be interesting for your job, look for convolutional neural networks. And just another output from this paper is like, these are the palms on some small subset. And when we look to the whole landscape, we see this distribution of palms, and we may do some analysis with that. Oh, locations with more palms, perhaps they are more disturbed. We want to protect that or not. Or maybe we want to go there and grab some acai fruit to eat. I don't know, to extract the fruits from these palms. So you and this thing with deep learning is that if you can see it on one image, deep learning can very likely map it. So this is what I'm saying. It's not proof, but usually it works like that. This is from another perspective, another work looking for palm trees. Right now, in this work, I used LiDAR data. So the same LiDAR data set that I showed before, the 600 and something. But now we see that we have this 3D information, and we see very, very good, very, very precisely the crowns. And you can use these methods to map. For example, I went from 7,000 palms that I delineated to more than 1 million palms over all the Brazilian Amazon. And when we can make maps like this, like to say, oh, this region of the Amazon has much more palm in the top of the forest than the others. This may be interesting to understand those forests. And you can do that to other kind of data. I showed this example, but it's used to other kind of data. Here's an example with building segmentation. The same kind of models, the UNet. This is a different approach to UNet, but you can use that to map buildings. You can use that to map solar panels. You can use that to map pools. You can use that to map trees inside the city. Anything you can see in the image, basically, you can probably map it. Perhaps this antenna over here. Maybe this is interesting for you. You can probably map that as well, if you have enough examples of that. All right. And I'm reaching towards the end. Don't be scared. One important thing when we talk about deep learning specifically is that in all other stuff that we worked before in the past, we use the CPU, is the processor that on our computers. But with deep learning, we have to use the GPU, which is the graphics card, like GeForce, NVIDIA GeForce something. Uh, why? Because the CPU is like a very fast car, but it can only carry like 4 people or 2 people perhaps in this car. But the GPU is like a truck, and it can carry lots of small things at once. It goes slower on in comparison to this Ferrari, but it carried lots of more weight than the Ferrari. So GPU is like this truck, and we can speed up the computation to actually be able to do the deep learning because of the GPU, because it's like millions of calculations. So if you want to go work with deep learning, you have to start looking for how to use the GPU and all of that. If you want now to look more at deep learning, you can take a screenshot of this screen, or write down afterwards. You get this link. There's this course that I provided for also for the IEEE last year. There's this GitHub page with examples with this code on Google Colab. You can watch the YouTube video for the course to learn more about deep learning, how to apply it. And another, probably one of the last examples, is about agriculture. You can use this data. For example, this is PlanetScope data, which is more high resolution. You have about 3 to 5 meter resolution, and you can use that to map crops, different types of crops, and to track how the crops are doing over time. Perhaps your company is interested in management. Okay, that farmer is paying for my company to say, okay, look at all my farms and say if it's going well, or maybe there's a plague, maybe there's some region of the image of the location that it's doing worse. I have to go there and put some nutrients on the soil. So you can use remote sensing to do that as well. And this is part of machine learning to estimate a biomass index, like how much the crops are growing, and tracking that over time, more like a time series problem. And here are some maps in relation to that crop yield management zones. Perhaps there's greener zone have more productivity, the other have less productivity. You have to go here and put some nutrients, take better care of your location. Also related to crops, and also first you have drones, and you can use that to track the forestry growing, to monitor crops, to find key species for conservation, and to measure the forest. For example, someone pays you to measure how much forest do I have in my property. You can go there and measure with the drones and this kind of stuff. Now, probably 5 slides left. A bit of my current research for you to know where I'm heading right now. I'm working with tropical forest degradation, which is there's lots of type of degradation going on, but 2 of those is logging and fire. So my goal right now is to map these 2 types of degradation. So if I look in these images, I see, okay, here there's something different. There are some roads, there are some soil. What are these? So this is when people go inside the forest, they cut down some trees, open these spaces to drop the logs, the trees that they cut down. These are called log decks. And they grow them, cut the trees and put those there. And there are a lot of this logging in the Brazilian Amazon, which are illegal. And I want to map that. I want to map those in order to help combat the forest crimes, and also to better estimate the carbon emissions. So how much carbon are we losing through this degradation? So mapping maps like this is the current aim of my research, and you may see something going publication probably later this year or something. And this is the last slide. And so just to finish saying that all this big remote sensing data that I was talking about, it's overwhelming, a lot of stuff. It requires big skills, and that's the part where you are probably right now. You're undergraduate, doing your bachelor's or your graduate student doing your master's or PhD, it's the time to gather skills. Scientific programming language such as R, which is what I use, but also Python. These are probably the two most common used in the industry and academia. So take some courses, really learn this if you want to work with this kind of data, because it's nowadays it's so much data. You need to use programming to be able to work efficiently, and also with other frameworks such as parallel processing to speed up the computations, cloud computing such as Google Earth Engine, very important, and high performance computing, a bit less important than the others, but if you work on a university, you may have access to this, or it's like supercomputers. It's not very common, but something else useful. And lastly, the analytical skills, the knowledge about the problems. So this is what you bring usually from your bachelor's, but like you're studying again, but go back to the solar panel thing about energy. This is the knowledge about the problem, and that you bring that. It's very important, because otherwise you just know how to do computing. You don't know about anything about the knowledge. You cannot do much stuff. You need the knowledge about the problem. And a few techniques such as time series analysis and spatial modeling, also very important. So I would say programming language, uh, a few types of different spatial analysis, such as from machine learning or deep learning, and lastly, creativity to put them all together, and that's when you make something real nice to come up. So thank you for watching me. I think I went 10 minutes past the time, but if you have questions, you can write on the chat. You can also email me. Look my Twitter account. I post some stuff about Earth observation, some cool papers going out, and that's it. Lizardo.
Thank you, Ricardo, for that wonderful presentation. It was really, it brought a lot of knowledge and a lot of subjects that we can use also over here, and a lot of raising awareness about the possibilities of big data also, and all of the algorithms that we can use, like convolutional networks and everything. A lot of people over here are kind of, it's trending over here now, pulling to those, but we have a long way to go still. So we'll begin the questions and answers segment. And for the attendees, you can write a question in the comment in this chat, and I will proceed to read it. Also, if you have a question in Spanish, you can write it in Spanish, and I'll try to translate it so that Ricardo can answer it. And I think we have a first question. It's from David Gomez. David Gomez says, "Thank you for the knowledge that you have shared with us. I have a question. Where can I find open source databases to work with, or how can I obtain satellite information in raw data to use them with my scripts? And if there are no open source databases, which sources do you recommend that are better?"
All right. Thank you, David, for the question. There is a trend on new open source databases of all types of images, and the labels for that. Imagine if it's a segmentation problem, you have like the images for the buildings and the mask saying, oh, this is a building, this is not a building. There is a trend to, this is something that's coming up. You can find like I do not know the specific GitHub for that. It's much more common for other types of computer vision, but it's starting to grow. I may have to find something and give you that afterwards. But the raw data, I think the main source would be the Google Earth Engine. You can go into the Google Earth Engine. Those are all open data. You can build scripts on either R or Python to automatically download those images, and then you can apply your own code on your computer. I think this is the main open source of data.
Okay, thank you, Ricardo. We have another question. It's from Manuel Olivares. Manuel says, I want to learn more about data science, specifically Earth data science. Where do you recommend starting? Is there any learning path that you know that is the best to follow? What can you recommend to me?
Thank you, Manuel. I think depends a lot on your background, but I think if you want to be a data scientist, you need to know how to program. That's 100% required. And then there's a lot of paths for Earth data. Uh, Perhaps pursuing some kind of specialization, such as a master's in some kind of GIS program or remote sensing program, to learn more about the data, to really understand how the data is acquired by the satellites. Like, for example, before I entered my master's, I already was working with some images, but I had no idea how those images were generated. And when you go and learn, okay, this is captured by a radiometer, capture the radiance, how this goes to the final data, you really understand what is the capability of the data. I do not know any online course for that, but um, probably some specialization, some university for on GIS, on remote sense is probably the best path to really specialize on that. Like in Brazil, like we have the INPE, the Masters in Remote Sensing. It's one of the more excellent places to do that.
Maybe following up with the question from Manuel Ricardo, for chemical engineering, kind of like how can chemical engineering fit in the world of geospatial data science
All
or
right.
so? Mhm.
There are data sets that track, for example, I see very fast a thing pop up about air quality. Is it the same question?
No, that will be
Not the
another
same
one, but
question.
yeah, but
All
we'll
right,
read
but
it.
I think it could be related. For example, air quality. You can there are data for air quality uh, of particulate matter that are spread in the air that you can have it to study in a regional way, like or continental or a country. You can then look at that data and see how it connects to the cities and all of that. So there is data. One of data sets I remember is the it's PM 2.5. It's the name of the layer. I don't recall the exact name of data set, but if you type in, for example, PM 2.5 spatial data, you likely find that on Google.
Okay, thank you. That was the air quality question was from Amara Asif. She was asking kind of like, can deep learning be used for air quality monitoring also?
Yeah, so that was the question I looked before. So, for example, for air quality, um, I do not know more about what kinds of data is available. In the end, depends on what data is available, right? So, for example, this data that I was talking about, the PM 2.5, that I know that it's available on a gridded scale. It relates, for example, to fires. If you have fire, you increase the amount of particulate on the atmosphere. You can relate to that, and you can relate that to health issues. I've seen there are papers doing that. I remember some from Brazil. Um, you could do the same thing, but then that depends on what's the source of of that damage to the quality that you're looking for. Um, and the deep learning or any machine learning actually can help you with tracking, doing these relationships between how this variable that you are looking, that represents the air quality relates to other factors in the environment, in the climate, in the weather, that you can use then to predict the air quality, right? So to connect these things.
Thank you. That's quite interesting. It's really helpful nowadays that we have a lot of emissions going up. We have a question from Shubham Kumar. Uh, ask, how can LiDAR data be helpful for forest wetlands?
I never did much research with wetlands. There is, if you're specifically interested in forest wetlands, there is this very amazing researcher called Thiago Sana, Thiago Sana Freire. I don't recall if it's Freire Sana or Sana Freire. With most of his work is on wetlands. Take a look on that. You see uh, different types of analysis with wetlands, with different types of data. I know that radar, like SAR, synthetic aperture radar, SAR, the SAR has been used a lot for wetlands to see areas that are flooded, seasonally flooded, not flooded at all. Um, I don't recall specifically about LiDAR being used to that. One point is because LiDAR also has a wavelength. So the signal that the sensor emits also has a wavelength. And usually the wavelength that the LiDAR uses is the near infrared. And near infrared, let's put this way, it doesn't like water. It doesn't reflect much out of water. So if you go and use get an LiDAR data over a wetland, you may have lots of missing data when the beams hit the water. You may miss lots of data. So yeah, I mean, I don't know much about this. I would expect that there are some challenges on doing that, but it's definitely something to look after. And also, sorry, and also for Brazil, if you're interested in looking at forest, wetlands, and LiDAR, with airborne LiDAR, like this one that I'm showing on the screen here, we have lots of wetlands and floodplains in Brazil, and there is LiDAR over that. So maybe you want some data over floodplains to look at. Send me an email, we can talk about that.
Thank you, Ricardo. We have another question. It's from Michelle Cruz. She says that I've been studying by myself, learning about data science, specifically Earth data science. I've been learning from earthdatascience.org. Is there any open source or resource that you have knowledge that you recommend? No?
Well, I think this is connected to the previous one of the previous questions. I currently do not know any open source data sets specifically for Earth observation. But if you guys find that, please email me.
Okay, thank you, Ricardo. We have another question also from Michelle. She says, I believe to be able to learn something new or get something new, you have to keep your mind stimulated. Feed yourself with the type of content that you are interested in and you like. So, do you know of any social media accounts that you recommend following or watching?
Yes. So I started going on Twitter last year to look more at specifically science. So I do not look much for other stuff and like haters and all of that we know that Twitter is full of. But I think Twitter is a nice place, and there are some pages like. One of those is Ladies of Landsat, which is a page run by women that share usually papers using Landsat data, Landsat satellite data. So look for Ladies of Landsat. It's very cool. This is what I remember from Twitter. From from YouTube, there is one channel that I like very much, which is focused on deep learning, and I learn a lot. Let me find it. It's Digital Serenity. Digital Serenity. I will put the link on the StreamYard. I hope the organization can share that. You can do that, Lizardo?
Yeah, I think we can. Yeah.
Yeah. Try to put that on the screen. Digital Serenity. It's the name of the guy. So this page, okay, I think I can put that on in the front of my screen as well. Let's try that. Yeah, this is the channel, Digital Serenity. So this YouTube, like, he has so many videos. You can see that I've watched a bunch of them. There's all these red things here. He teaches about deep learning, and he's very, very good. So definitely look for this. It's Digital Serenity. He teaches with Python. So I don't use Python, I use R, but it's the same concept, the same frameworks. You can definitely use the knowledge, and you can follow his steps. He shared the codes. He shared the data that used for the codes. Yeah, probably the best the best data set and codes you can find for deep learning. And he shows applications for magical images, for let's say for any images like faces or anything. It's very good.
Thank you, Ricardo. I have one question myself also.
All right.
It's when you've been studying about deforestation, have you also, or has there been done any research on how the temperature rises on spaces where deforestation compared to other places when they are not?
Yeah. I think there's a researcher. There is research looking at both temperature and also rainfall. So how deforestation modifies that. Um, trying to find the paper. I think it was Eduardo Maeda, the name of the guy. Um, let me share this with you. Take a look after for Eduardo Maeda. I think he has some papers on that. But the overall understanding is that if you remove forests, you remove the pump that takes out water from the soil and throws it back to the atmosphere. So you have less water vapor on the atmosphere. You have it increases the temperature locally and reduces the rainfall as well. So this is like more or less the common understanding. So this researcher is very good about this kind of environmental studies.
Thank you, Ricardo. We have a question. I guess this will be the penultimate one. It's from Ken Kuchia. Hi, I have a question about machine learning. How can it identify human face if it can identify human faces, then it could also identify specifically types of crops or flora in a forest?
All right. That's more or less what I was talking about, the palm trees. Like, for example, if like the examples I showed, we could see the palm trees because they were little stars in the middle of the forest. We can see that, we can identify that. Usually, if it's not easily identifiable by eye, it may be a bit harder to do that. But there are lots of efforts doing that with usually more simple methods, not more simple, but with machine learning, not deep learning, like random forests or support vector machines. If you have data on different tree species, like imagine this crown here is from one species, these other crowns another species, these other crowns another species. You go to the field and you know that for sure, and you can find that on the images. And then you have like high resolution optical images from worldview, GOI, on those locations, that you have like several spectral bands. Then you can see if those species, those crowns, are separable between these spectra. So perhaps one species has more near infrared or more or less red signal. You can do that. One good researcher to look specifically for that is I forgot the name of the guy. It's Ferreira. Mateus Ferreira. How I forget the name of my friend, Mateus Ferreira. Ime. So Mateus Pinheiro Ferreira. When I say the name of, for example, these researchers, you may Google the name of the researcher and add scholar to the site. If you do that, let me show you real fast this. Like for example, I Google the name of the guy, and then I add scholar and I find it here, and then I can click and see the publications. I don't know why this is in German, but okay. All right, then you can see the publications with more citations. So we have to trust this is written citations here, and this is year, and you can see the most citations. Let's look up mapping 3 species. So the most cited paper from this researcher is about that, because he worked a lot of that. And if you click on year, you may see the latest papers. So let's say large-scale fuel load characterization. So with JEDI data, they want to see how much fuel there is in the forest that can burn, or forest diversity. Yeah, he works a lot of that. So yeah, you can do that. And going back to the question, we train these models by example. So you need to have samples, examples for each to learn. If you don't have many examples, then it's hard to do it. You need to have examples. In that GitHub that I showed, it's a bit back on my presentation. Here, you may find on this GitHub, there is an example that I did for this short course on the EEE last year, that is mapping rice. So it's one specific type of crop that we can map with deep learning. So you take a look on there and you see how I did that.
Okay, Ricardo, thank you for answering the question. That would be the last one. In honor of the time, we will close the question space. So thank you very much for all of the attendees for your participation. We regret not being able to answer all your questions, but I think we did most of them.
Oh yeah, I think it was very good.
Yeah, many good questions.
Yeah, it's good when people ask questions, and it really feels like they are really interested in learning more, and that's good.
Yeah, it's really good. These types of subjects are always very interesting in all of the applications. So I'll proceed to read your diploma. The EEE Geoscience and Remote Sensing Society student chapter of the Universidad del Salvador, or University of El Salvador, GRSS-US, grants this recognition to Ricardo Dalagnol for his participation as a speaker in the webinar entitled Remote Sensing Applications for Environment and Sustainability, San Salvador, April 29, 2022. It's signed by Citar Galdames, the chair of the EEE GRSS US branch, Rodrigo Velasquez, chair of the GIS and Remote Sensing Club, and the Master in Science, Carlos Pocasangre, which he is our counselor. So thank you very much. Ricardo, I don't know if you have any last words. to give to
just
us?
to thank you for the invitation, and also the whole organization of the EEE event. I think you guys are doing an awesome job. Keep doing that. Very good.
Thank you, Ricardo. So we also thank each one of you for your presence in this webinar. Do not forget that you can find the recording of this webinar in our YouTube channel, the EEE GRSS YouTube channel also. Y en español, muchas gracias a todos por los que atendieron a este webinar. Les agradecemos mucho su presencia y por la cantidad de preguntas que hubieron también. Creo que tenemos una última noticia que dar. Sobre la visita técnica al planetario del Observatorio Micro-Macro de la Universidad Don Bosco, que se llevará a cabo el viernes 13 de mayo. El punto de reunión será en la gasolinera Puma, frente a la entrada de la Facultad de Economía UES. La inversión es, si usted es miembro de IEEE, GRSS UES, es un precio especial, y para público general de $25. Cualquier consulta las puede enviar al correo de nuestro capítulo. Muchas gracias.
Muchas gracias. Chao.
Thank you, Ricardo.